Hello everyone, welcome back to the CSC Guy. Today we are diving into two fascinating areas of artificial intelligence, knowledge representation and machine learning. We will explore ontological engineering, categories, reasoning, and various machine learning concepts, including classification and decision trees. So let's get started. First, let's discuss the role of ontological engineering in artificial intelligence. Ontological engineering involves the creation and management of ontologies, which are formal representations of knowledge within a specific domain. In artificial intelligence, ontologies help in structuring information, enabling machines to understand and reason about the data they process. The key roles of ontological engineering include knowledge sharing. Ontologies provide a common vocabulary for different systems, facilitating knowledge sharing and interoperability. Second, knowledge representation. They allow for the representation of complex relationships and hierarchies among concepts, making it easier for artificial intelligence systems to process and infer new information. Third, reasoning. Ontologies enable reasoning about the properties and relationships of concepts, allowing artificial intelligence systems to draw conclusions based on the structured knowledge. Fourth, semantic web. In the context of the semantic web, ontological engineering helps in creating a more meaningful web by enabling machines to understand the context of information. In summary, ontological engineering is crucial for building intelligent systems that can effectively reason and make decisions based on structured knowledge. Next, let's discuss how categories and objects are represented in a knowledge base. In a knowledge base, categories are often represented as classes or types, while objects are instances of these classes. For example, a category like animal can be represented as a class that includes properties such as has legs, can eat, and can move. Second, objects. Specific instances of this category like dog or cat would inherit these properties. For instance, a dog object might have the property has legs set to 4 and can bark as a specific behavior. This hierarchical representation allows for efficient organization and retrieval of knowledge, enabling reasoning systems to infer relationships and properties based on the categories and objects defined in the knowledge base. Next, let's discuss the significance of mental events and mental objects in reasoning. Mental events refer to cognitive processes such as thinking, believing, or remembering, while mental objects are the concepts or ideas that exist in our minds. The significance of these concepts in reasoning includes: first, understanding human-like reasoning. By modeling mental events and objects, artificial intelligence systems can simulate human-like reasoning processes, making them more relatable and effective in tasks like natural language processing. Second, knowledge representation. Mental objects help in structuring knowledge, allowing systems to represent complex ideas and relationships, which is essential for effective reasoning. Third, inference. Mental events can trigger inferences based on existing knowledge. For example, if an AI system remembers that all humans are mortal and Socrates is a human, it can infer that Socrates is mortal. In summary, mental events and objects are crucial for developing AI systems that can reason and understand the world in a human-like manner. Now let's provide examples of how reasoning systems use categories for inference. Consider a medical diagnosis system. It might have categories like disease, symptom, and treatment. Example 1. If the system knows that fever is a symptom of flu and flu is a type of disease, it can infer that if a patient has a fever, they might have the flu. Second example, in a shopping recommendation system, categories like electronics, clothing, and books can help infer user preferences. If a user frequently buys items from the electronics category, the system can recommend new gadgets based on that category. These examples illustrate how reasoning systems leverage categories to make informed inferences and decisions. Now let's discuss reasoning with default information. Reasoning with default information involves making assumptions based on typical or common knowledge when specific information is not available. This method is particularly useful in situations where complete data is not accessible, allowing systems to make educated guesses. Scenario: consider a smart home system that controls lighting. If the system knows that most people turn on lights when it gets dark, it can default to turning on the lights at sunset unless that user has specified otherwise. In this case, the system uses default reasoning to enhance user experience by anticipating needs based on common behavior patterns. This approach can also be applied in various domains such as customer service chatbots that assume typical customer inquiries and provide default responses unless specified otherwise. Moving on to machine learning, let's discuss the different types of attributes. First, nominal attributes. These are categorical attributes without any intrinsic ordering. For example, color can be red, blue, or green. Second, ordinal attributes. These attributes have a clear ordering but no fixed interval between values. An example is customer satisfaction, rated as low, medium, or high. Third, interval attributes. These have meaningful intervals between values but no true 0 point. For instance, temperature in Celsius is an interval attribute. Fourth, ratio attributes. These have both meaningful intervals and a true 0 point, allowing for a full range of mathematical operations. An example is weight or height. Fifth, binary attributes. These are a special case of nominal attributes with only two possible values, such as yes or no. Sixth, continuous attributes. These can take any value within a range, such as age or income. Understanding these attribute types is crucial for selecting attribute algorithms and processing data effectively. Next, let's discuss how to estimate missing values in datasets. One common method is mean imputation, where you replace missing values with the mean of the available values of that attribute. Example: suppose we have a dataset of student scores 85, 90, one is empty, 80, 95. To estimate the missing value, we calculate the mean of the available scores. 85 plus 90 plus 80 plus 95 by 4, which is equal to 87.5. We then replace the empty score with 87.5, resulting in the updated dataset. While mean imputation is simple, it can introduce bias, so it's essential to consider other methods like median imputation or using predictive models for more accurate estimations. Now let's define classification in the context of machine learning. Classification is a supervised learning technique where the goal is to predict the categorical label of new observations based on past observations with known labels. The process involves training a model on a labeled dataset where each instance is associated with a specific category. For example, in email filtering, the model is trained on emails labeled as spam or not spam. Once trained, it can classify new emails into these categories based on learned patterns. Next, let's differentiate between supervised, unsupervised, and reinforcement learning. Supervised learning. In this approach, the model is trained on labeled data, meaning each training example is paired with an output label. The goal is to learn a mapping from inputs to outputs. Unsupervised learning. Here, the model is trained on data without labeled responses. The goal is to identify patterns or groupings within the data, such as clustering similar items together. Third, reinforcement learning. This type involves training an agent to make decisions by taking actions in an environment to maximize cumulative rewards. The agent learns through trial and error, receiving feedback based on its actions. Each of these learning paradigms serves different purposes and is suited for various types of problems. Now let's explain the naive-Bayes classification algorithm. Naive-Bayes is a probabilistic classifier based on Bayes' theorem, which assumes that the presence of a particular feature in a class is independent of the presence of any other feature. This naive assumption simplifies the computation of probabilities. The algorithm works as follows. Calculate the prior probability of each class based on the training data. Second, calculate the likelihood of each feature given the class. Third, use Bayes' theorem to compute the posterior probability for each class. Fourth, assign the class with the maximum posterior probability to the new instance. Despite its simplicity and the strong independence assumption, naive Bayes often performs surprisingly well in practice, especially for text classification tasks like spam detection. An excellent example of a real-world application of naive Bayes is in email spam filtering. In this scenario, the algorithm analyzes the words in incoming emails and calculates the probability of the email being spam or not based on the frequency of certain keywords. For instance, if an email contains words like free, win, or offer, the naive Bayes classifier can determine that it is likely to be spam based on the learned probabilities from previously labeled emails. This method is efficient and effective for handling large volumes of emails. Now let's discuss the process of constructing a decision tree. First, selecting the best attribute. The first step is to choose the attribute that best separates the data into classes. This is often done using metrics like Gini impurity or information gain. Second, create a node. A node is created for the selected attribute and branches are formed for each possible value of that attribute. Third, split the dataset. The dataset is split into subsets based on the values of the chosen attribute. Fourth, repeat. The process is repeated recursively for each subset, selecting the best attribute at each step until one of the stopping criteria is met, such as reaching a maximum depth or having all instances in a subset belong to the same class. Fifth, pruning. After the tree is constructed, it may be pruned to remove branches that have little importance, which helps to reduce overfitting. Let's now discuss the advantages and limitations of decision trees. Advantages: easy to understand. Decision trees are intuitive and easy to interpret, making them accessible for non-experts. Second, no need for data normalization. They do not require normalization of data as they can handle both numerical and categorical data. Third, feature importance. Decision trees can provide insights into the importance of different features in making predictions. Limitations: first, overfitting. Decision trees can easily overfit the training data, especially if they are deep and complex. Second, instability. Small changes in the data can lead to different tree structures, making them less stable compared to other algorithms. Third, bias towards dominant classes. They can be biased towards classes that have more instances, which can affect the performance on imbalanced datasets. Next, let's explain the concept of pruning in decision trees. Pruning is the process of removing sections of the tree that provide little predictive power to reduce complexity and improve generalization. There are two main types of pruning: pre-pruning and post-pruning. In pre-pruning, this involves stopping the tree from growing when it reaches a certain condition, such as maximum depth or minimum number of samples in a node. Second is post-pruning. This occurs after the tree has been fully grown. Nodes are removed based on their contribution to the overall accuracy of the model, often using a validation dataset to access performance. Pruning helps to combat overfitting and can lead to a more robust model. Pruning affects both the accuracy and complexity of a decision tree. How it affects the accuracy? It affects accuracy by removing branches that do not contribute significantly to the predictive power. Pruning can improve the model's accuracy on unseen data. It helps to ensure that the model generalizes better rather than memorizing the training data. How it affects complexity? Pruning reduces the complexity of the decision tree, making it simpler and easier to interpret. A less complex model is often more desirable, as it can be more efficient in terms of computation and easier to explain to stakeholders. Now let's discuss rule extraction in classification trees. Rule extraction involves converting the decision tree structure into a set of if-then rules that can be easily understood and applied. Uh, each path from the root to a leaf node can be translated into a rule that describes the conditions under which a particular class is predicted. For example, if a decision tree has a path that leads to a tree leaf node indicating approved for a loan application, the corresponding rule might be if the applicant's income is greater than $50,000 and the credit score is above 700, then the loan is approved. This process makes the model's decisions more interpretable and allows for easier communication of the logic behind predictions. Let's now explain the process of extracting rules from a decision tree with an example. Consider a simple decision tree used for classifying whether a person will buy a product based on their age and income. The tree might have the following structure. First is, if age is less than 30 and income is greater than $40,000, then buy is equal to yes. Second, if age is less than 30 and income is less than or equal to $40,000, then buy is equal to no. If age is greater than or equal to 30 and income is greater than $60,000, then buy is equal to yes. If age is greater than or equal to 30 and income is less than or equal to $60,000, then buy is equal to no. To extract roots, we follow each path from the root to the leaf node. Each path corresponds to a rule that captures the conditions leading to a specific classification. In this case, we would extract the following rules. First, if age is less than 30 and income is greater than $40,000, then buy is equal to yes. Second rule, if age is less than 30 and income is less than or equal to $40,000, then buy is equal to no. Third, if age is greater than or equal to 30 and income is greater than $60,000, then buy is equal to yes. Fourth, if age is greater than or equal to 30 and income is less than or equal to $60,000, then buy is equal to no. These rules can then be used for making predictions on new data, providing a clear and interpretable decision-making framework. Finally, let's compare naive Bayes and decision tree classifiers in terms of performance and use cases. Performance. Naive Bayes is generally faster and requires less training data, making it suitable for large datasets. It performs well in text classification tasks such as spam detection, where the independence assumption holds reasonably well. Decision trees, on the other hand, can capture complex relationships in the data but may overfit if not pruned properly. They are more interpretable and can handle both numerical and categorical data effectively. Second, use cases. Naive Bayes is often used in applications like sentiment analysis, document classification, and medical diagnosis. Decision trees are widely used in scenarios requiring clear decision-making processes such as credit scoring, customer segmentation, and risk assessment. In summary, the choice between naive Bayes and decision trees depends on the specific problem, the nature of the data, and the importance of interpretability. For a dataset with categorical features, I would choose the decision tree classifier. The reason is that decision trees can naturally handle categorical data without the need for encoding, making them more straightforward to implement in such cases. They also provide clear decision rules that can be easily interpreted, which is beneficial for understanding the model's behavior and communicating results to stakeholders. Additionally, decision trees can capture interactions between features, which can be crucial for making accurate predictions in datasets with complex relationships. So that's it for today. Thank you for joining me today on the CSE Guide. We have covered a lot of ground from knowledge representation in AI to various machine learning concepts. I hope you found this information helpful and engaging. If you have any questions or topics you would like me to cover in future videos, please leave a comment below. Don't forget to like, subscribe, and hit the notification bell for more content. See you next time.